Today, we're going to be looking at the world of engineering simulation.
Oh, yeah.
We're going to be focusing on two pretty cool techniques, finite element analysis, FEA,
Yeah.
and computational fluid dynamics, or CFD.
CFD.
Basically, these are tools that let engineers predict how things behave in the real world
Right.
before they even build them.
It's kind of like peeking into the future, isn't it? A digital crystal ball.
Yeah, that's a good way to put it. So let's start with FEA.
Okay.
One of our sources describes it as breaking a big object into tiny pieces.
Right, like puzzle pieces.
Yeah,
To see how they react to different forces.
exactly.
So imagine you're building a bridge.
Okay.
With FEA, we can create a virtual version of that bridge.
Okay.
Not with steel and concrete, but with equations and algorithms.
So we can digitally stress test this virtual bridge.
Exactly. We can simulate all sorts of loads like wind, traffic, even earthquakes.
Wow,
And the software shows us how the bridge would respond.
that's incredible.
Yeah, we can see where the stress concentrates, any potential weak points,
Uh-huh.
and then make design changes before we even start construction.
So it's all about making structures safer, more robust, right?
Absolutely. But it's not just about safety. FEA can also help us optimize designs.
How so?
Well, we can make things lighter, stronger, more efficient.
Okay.
One study mentioned a car company that used FEA to redesign their chassis.
Uh-huh.
They reduced its weight by 15%.
Wow, and that means,
Better fuel efficiency.
Right.
Lower emissions.
so there's a sustainability angle as well.
Exactly.
I'm kind of curious, though, how does this virtual breaking down of an object actually work?
Yeah.
The source material mentioned something called meshing.
Ah, yes. Meshing.
What is that?
It's a key step in FEA. We divide that digital model into smaller elements.
Okay.
Those tiny pieces you mentioned earlier.
Like a 3D jigsaw puzzle.
Yeah, kind of. These elements can be different shapes and sizes.
And so the more pieces, the more accurate the simulation.
Generally, yes, but it also requires more computing power.
Ah, so there's a trade-off there.
Always.
Okay, so we've got our mesh.
Right.
What's next?
We need to define the boundary conditions.
Boundary conditions.
Yep, these tell the software how the object is constrained or loaded in the real world.
Like where a bridge is anchored to the ground,
Exactly.
or how much traffic it's expected to carry.
Those are constraints. We also need to apply loads, like the weight of vehicles or the force of wind.
I see. So we're basically setting the scene for the simulation.
Right. We're telling the software what the real-world conditions are.
It's not as simple as I thought.
No, it's quite involved.
So once the boundary conditions are set,
Then the fun begins.
what happens?
The software uses these powerful algorithms to calculate how each tiny element will deform and how they'll interact with each other.
We're basically giving the computer a super challenging physics problem to solve.
That's a great way to think about it.
And the solution to this problem helps engineers make better decisions. It's like seeing inside the structure, right?
Yeah, like having X-ray vision.
We can see stresses and strains.
Things we couldn't observe in the real world.
And this leads to what?
Safer designs,
Yeah.
more efficient structures, lighter materials.
Which ultimately benefits the environment.
Exactly.
FEA seems incredibly versatile.
Oh, it is. It's used in so many industries, from aerospace to automotive to even medical devices.
It's amazing how it can be applied to such a wide range of problems.
It really is.
But I imagine there are limitations as well, right?
Of course. No simulation is perfect.
Right.
The accuracy of FEA depends on a lot of factors.
Like what?
The quality of the mesh, the accuracy of the material properties, the assumptions made about the loads and boundary conditions.
So it's a powerful tool, but we can't just blindly trust the results.
Exactly. Engineers need to interpret those results, understand the limitations.
And make informed decisions based on their expertise.
Precisely.
FEA seems like it requires a deep understanding of both the engineering principles and the software.
It does. It's a specialized field.
But the benefits are undeniable.
Absolutely.
FEA has revolutionized how we design and analyze structures.
For sure, it's led to safer, more efficient, and more innovative products.
Well, now that we've explored the world of solid objects and forces,
Right?
how they behave under stress,
Mm-hmm.
now let's move on to fluids
Okay.
and dive into the world of CFD.
Right.
What I find fascinating about CFD
Yeah.
is its ability to visualize stuff that we can't actually see,
Uh-huh.
like the swirling patterns of air around a moving car
Right.
or the currents in a river.
Exactly. It gives us a view into fluid behavior that we wouldn't get from just physical experiments.
Right.
Imagine trying to measure the velocity and pressure at every single point in a complex flow.
Yeah. That would be.
It'd be incredibly difficult.
And time-consuming.
For sure.
Our source material mentions CFD being used to design more aerodynamic cars.
Okay.
Can you explain how that works?
Sure. Let's say you're designing a new car.
Okay.
And your goal is to minimize drag.
Drag.
The resistance it encounters as it moves through the air.
Aye.
Reducing drag is super important for fuel efficiency.
Makes sense.
And lowering emissions.
So where does CFD come into play?
Well, with CFD, we can basically create a virtual wind tunnel.
Oh, that's interesting.
We begin with a digital model of the car, and then we define the properties of the air, things like its viscosity and density.
Okay.
We also set boundary conditions, like the speed of the oncoming airflow.
Okay.
And the conditions at the car's surface.
But we're essentially telling the software how the air is interacting with the car.
Exactly. We're setting the stage.
When what?
The software takes over. It uses these sophisticated algorithms to solve complex equations that describe the motion of the air. These equations are based on some pretty fundamental laws of physics, like conservation of mass, momentum, things like that.
And the output of these calculations.
We get this detailed picture of how the air flows around the car.
Interesting.
We can see areas of high pressure,
Okay.
low pressure, where the flow separates from the surface, where vortices form, all that good stuff.
And this information can then be used to refine the design of the car.
Exactly. Engineers can use these insights to tweak the car's shape, smooth out sharp edges, add spoilers,
Right.
modify the underbody, all to reduce that drag.
So CFD has played a big part in making cars more aerodynamic.
Oh, yeah. Huge.
Much more so than their older counterparts.
Definitely.
I think our source material also talked about using CFD in aerospace.
Yeah.
Specifically for designing airplane wings.
Right. That's another big area where CFD shines.
How so?
By simulating airflow over a wing, engineers can pinpoint areas of high drag.
Okay.
And they can optimize the wing shape.
To improve what?
To improve lift and to reduce fuel consumption.
Ah, I see. Making air travel more efficient.
Exactly. More sustainable, too.
CFD seems like it has a wide range of applications.
Oh, it does. It goes way beyond just cars and airplanes.
Yeah.
It's used to design more efficient wind turbines.
Oh, cool.
To optimize the flow of liquids in pipelines. Even to model how pollutants spread in the atmosphere.
So it's a very versatile tool.
Very versatile.
Now, since both FEA and CFD involve creating digital models and simulations,
Yeah.
I'm curious about the setup process.
Okay.
How does it compare between the two?
Well, there are some similarities.
Mm-hmm.
Just like in FEA, we start with a digital model of whatever we're analyzing.
Okay.
And we also break that model down into smaller pieces.
But instead of finite elements,
In CFD, we use a mesh of cells.
so we're still breaking down the problem into smaller chunks.
Essentially, yeah, just different terminology.
And the quality of the mesh
Right.
affects the accuracy.
It does. The size and shape of those cells is important. It affects both accuracy and computational cost.
I see.
Choosing the right meshing strategy is crucial.
Right. And once we have that mesh, what's the next step?
We define the fluid's properties.
Okay.
Things like its viscosity and density.
So those properties dictate how the fluid will behave.
Exactly. And then we set boundary conditions as well.
What do those tell us?
They tell the software how the fluid is flowing in and out of the system.
So in our car example, we would specify the speed and direction of the wind.
Right. And the conditions at the car's surface, how smooth or rough it is.
Okay.
All those details.
So defining these boundary conditions accurately is pretty important.
Oh, yeah. It's crucial they provide the context for the whole simulation.
So once the mesh is created, boundary conditions are set.
Right.
The software can start crunching the numbers.
Exactly. It uses all those numerical methods and algorithms to solve the equations that govern fluid motion.
And those can get pretty complex.
Oh, they can be very complex, especially for detailed simulations.
Which means it requires a lot of computational power.
It does. Historically, that's been a limiting factor, but advancements in computing technology have made it easier.
So we can handle more complex problems now.
Yeah, for sure.
And what kind of output do we get from all these calculations?
The software generates a ton of data about the fluid flow.
Amazing.
We can visualize things like velocity vectors,
Okay.
pressure contours, temperature distributions, all sorts of cool stuff.
We can even track the movement of particles in the flow.
Yeah, you can do that too.
It's like having a microscope for fluids,
That's a great way to put it. We can see all these tiny details.
which helps engineers understand how the air or water is behaving.
Exactly. They can identify areas of high stress,
Okay.
turbulence. They can optimize designs, predict how the fluid will interact with different structures.
So both FEA and CFD give us this unique insight into things that are hard to observe in the real world.
Yeah, that's the beauty of simulation.
FEA is all about solids under stress,
Right.
and CFD tackles fluid flow.
Yep. Two sides of the same coin.
And both of them have really changed how we design and analyze systems.
Oh, yeah. They've made things safer, more efficient, more innovative.
But like any tool, I imagine there's some limitations to consider.
Of course, setting up and running these simulations can be complex.
In what way?
It requires specialized knowledge in both fluid dynamics and numerical methods.
Mm-hmm.
And like with FEA, the accuracy depends on a lot of factors.
The model, the mesh, the boundary conditions.
All of those. Yeah, it's not a set and forget kind of thing.
So human expertise is still essential.
Absolutely. Engineers need to understand the results, the limitations of the simulation.
And use that information to make informed decisions.
Exactly. It's a partnership between human and computer.
As we wrap up our look at CFD, I'm curious about the bigger picture.
Okay.
FEA and CFD are becoming more powerful, more accessible. How do you see them shaping the future of engineering and design?
That's a great question. And honestly, I think we're just scratching the surface. Yeah, computing power is increasing. Software is becoming more sophisticated. We'll be able to tackle more complex problems, simulate real-world scenarios with even greater accuracy.
It's really exciting to think about the possibilities. We've talked about designing lighter cars and more efficient airplanes.
Right.
But what other applications could we see on the horizon for these simulation technologies?
Well, one area that I find particularly exciting is bioengineering.
Oh, wow.
Researchers are actually using FEA and CFD to simulate things like blood flow through arteries,
Oh, wow.
the mechanics of heart valves,
Really?
even airflow in lungs.
It sounds like FEA and CFD are playing a pretty big role in advancing healthcare then.
Oh, yeah, huge role.
These simulations can help us understand these complex systems much better,
Exact.
diagnose and treat diseases,
Right.
maybe even design better medical devices.
For sure. It's really remarkable.
It is amazing.
And another area where I see huge potential is in sustainable design.
Okay, tell me more about that.
Well, we can use these tools to optimize the energy efficiency of buildings,
That makes sense.
design more effective renewable energy systems, even model the impact of climate change on different environments.
Wow. So FEA and CFD can actually contribute to a greener future.
Without a doubt, they can help us find solutions that are both good for the environment and make economic sense.
And as these technologies become even more user-friendly,
Right.
more accessible,
I think we'll see even more creative applications pop up.
it's pretty inspiring to think about the positive impact they can have.
It is. It's really quite powerful.
As we keep pushing the boundaries of what's possible with FEA and CFD, though,
Yeah.
it's important to keep in mind that they're just tools.
Right. Incredibly powerful tools, but still just tools.
Ultimately, they're in our hands.
Exactly. The responsibility is on us to use them wisely.
Then ethically.
Absolutely. We got to make sure that these technologies are used for the good of everyone.
And for the planet.
For sure. As we develop these really sophisticated simulations, we can't lose sight of the real-world implications.
That's a good point.
It's easy to get caught up in the technical details, but the impact on the real world is what matters.
I'm just left with this sense of awe at how powerful these tools are.
Me too.
But also a real appreciation for the human ingenuity behind them.
It's that human element that drives it all forward.
Absolutely. And thank you for taking us on this journey into the world of engineering simulation.
You're welcome. It was my pleasure.
We hope you've gained a new appreciation for the power of FEA and CFD
I hope so.
and the incredible impact these tools are having on our world.
It's an exciting field to be a part of.
It is.